Okay, so it is spin pair repulsion that phosphorus has unpaired orbitals, whereas sulfur you're removing electrons from a p subshell where one of the p orbitals is already paired. So because you're removing electrons from a paired orbital, the two electrons would be repelling each other, and there's going to be spin pair repulsion. So you have to explicitly write over here that the first thing is in sulfur, the first point is that in sulfur electron is removed from a paired p orbital. So it's removed from a paired p orbital uh, compared to an unpaired orbital in phosphorus. And the second point is that it's easier to remove electron because of spin pair repulsion. The two electrons would be repelling each other. So the second point is going to be that due to spin pair repulsion, it is easier to remove electrons in sulfur. The next part is sodium is a better electrical conductor than phosphorus. Uh, that's very obvious that sodium is metallic. That's the first point. Sodium is a metal. And you're going to describe the structure of a metal, that it has positive metal ions in a sea of free moving delocalized electrons. So it's a lattice of positive metal ions in a sea of free moving electrons, which is why it's going to conduct electricity. Meanwhile, phosphorus has no free moving. It's a non-metal. It has no free moving electrons. So phosphorus is simple molecular, which only has covalent bonds, no free moving electrons. The next part is magnesium is a better conductor of electricity than sodium. The reason is magnesium has more delocalized electrons, and you can also compare to sodium. So it's just 1 mark, so that should be sufficient. So this is in period 3, still continuing with period 3. I think the following chart below shows a series of reactions. There's Mg reacting with nitric acid. If we make an equation, a metal when it reacts with an acid, it produces two things. One is going to be a salt, so it's going to be MgNO3 twice, and the other thing that's going to be produced is going to be hydrogen gas. And you can balance this equation. So the two likely products are going to be these two. And as you can see, they clearly stated this. So this is MgNO3 twice. And the other one is H2 gas. And then they're saying that reagent X is added and a white precipitate is formed. And there's another reaction that's going on where MgNO3 twice is getting converted into MgO and H2O and two other gases. Now, one thing that you've studied is the decomposition of nitrates that produces gases. Uh, they are definitely adding heat, so that path, this is decomposition happening. And when a nitrate decomposes, especially a group 2 nitrate decomposes, it produces two gases. One is going to be NO2 gas and the other one is going to be oxygen gas. So two gases are going to be produced uh, because of the decomposition. Water is usually not there. The only reason they've added water over here is because it was an aqueous solution. Otherwise, the decomposition of nitrate doesn't contain water. Because it's an aqueous solution, that's why water vapors are present as well. And then they're also asking about the white precipitate. They're saying that a reagent X was added, uh, and they've talked about the identity of E over here. I think that E reacts with dilute aqueous acid to produce a gas that turns lime water milky, which means carbon dioxide gas. That's a test for carbon dioxide gas. So CO2 gas is being produced. Uh, and who produces CO2 gas? Carbonates produce CO2 gas. So the identity of E is probably magnesium carbonate. Because if you add aqueous acid to it, it's any acid. For example, if you add HCl, it's going to produce a salt plus water plus carbon dioxide. So E over here, because it's being formed from magnesium, it must be magnesium carbonate. How do you get how do you get E? What would be reagent X? Uh, E is a solid. That means ionic precipitation is happening. What is ionic precipitation? That you take magnesium nitrate aqueous. Since magnesium nitrate is aqueous, that means all of its ions are going to mix in water and they would dissociate. So Mg2 plus ions and NO3 minus 1 ions, they would be freely roaming around in aqueous state. So which compound would precipitate out magnesium carbonate? It has to contain carbonate, but the negative ion would not be existing alone. So make sure the other reagent is a soluble carbonate. For example, potassium carbonate. If it's potassium carbonate, group 1 carbonates are all soluble. So if you add potassium carbonate, that would also dissociate in aqueous state, and the ions would just be mixed around. They would be roaming freely, and two of these ions, they might join up like Mg and CO3, and if they join up, they would form a precipitate which is insoluble. So the ions would randomly uh, get attached to each other. Mg2 plus and CO3 minus 2 are insoluble. The reason they are insoluble is because the charges are very large, which is why they're going to attract each other, and which you already know in the solubility table that magnesium carbonate is a solid. And the reason why it's a solid is that the 2 plus and the minus 2 ions, they would be attracting each other very strongly. So they would all get together to form a crystal. Mg2 plus would attract CO3 minus 2 very strongly. K and NO3, they would not be attracting each other very strongly, which is why they are soluble in the first place. Group 1 compounds, the reason they're very soluble is that they easily dissociate. Uh, they can be dissociated in aqueous state, whereas ions that have greater charges, they attract each other very, very strongly, and they usually tend to form crystals, and they don't mix with water. So the precipitate of magnesium carbonate solid would be formed, and the identity of reagent X is you can say potassium carbonate, but it could be any carbonate as long as it's soluble. So K2CO3 aqueous, or it could be any soluble carbonate. Okay, is this clear? Binail, is this clear? Bazga, Ethan, Mohammed, is this clear?
Yes, sir.
Yes.
Now the next part is a moles question. So you're given that spathos is an iron ore that contains it's an iron ore that contains FeCO3. The percentage of iron 2 carbonate in spathos can be determined by titration and acidified potassium dichromate 6 solution using a suitable indicator, and the equation is given. So you're taking a 5 gram sample. When you have a big question of moles, make sure sketch something what's happening. TK, what's happening is there is a 5 grams sample of spathos, TK, which is an ore. So let's say there's this rock. The total mass is 5 grams. What does it contain? It probably contains FeCO3, which they've already said in the question. So it contains FeCO3 right at the beginning, and it's reacted with hydrochloric acid. So they're reacting it with hydrochloric acid. What's going to happen? FeCO3 in spathos would react with the hydrochloric acid and it would dissolve. It would form FeCl2, which is a soluble compound, plus it's going to produce water plus carbon dioxide, right? So it's going to dissolve and form a solution. So now you have a solution, and it's a 250 cm cube solution. They've already said that the filtrate was made up to 250 cm cube solution. So it's a 250 cm cube. They added distilled water, and now you have a 250 cm cube solution which contains FeCl2. And then you have they're taking 25 cm cube of this standard solution and they're titrating it with potassium dichromate 6. So from this solution, they are removing 25 cm cube and putting it in a conical flask. So it definitely contains Fe2 plus ions or FeCl2, and they're titrating it with what thing from the top. So from the top, they're adding from the burette. What are they adding? They're adding dichromate 6 solution. So that's Cr2O7, 2 minus. And they've given us the volume that's being used, and the concentration is also provided. That's the volume is 27.30 cm cube, and the concentration that they're using is 0.02 mole per dm cube. So this is all that's happening. The first part is you have to find the moles in part one. You have to find the moles of dichromate 6 uh, in the titration. So you have the concentration, you have the volume, you can find the moles. Can you even do the calculation? It's going to be moles is concentration times volume. So it's 0.02. 1 second. 0.02 into 27.3 divided by 1000. So what is the value that we're getting?
5.46 into 10 raised to the power minus 4.
ठीक है, minus 4 moles. And always remember that all the values are given up to 3 significant figures, so your answer should not exceed 3 significant figure accuracy. It can't be more accurate than the values that are given over here. The next part is you have to find the moles of Fe2 plus, which you can find because it's 1:6. That's given at the top. So you have the moles of Cr2O7. So the moles of Fe are going to be 6 times that. So what's a 5.46 into 10 to the power minus 4 multiplied by 6?
3.2
3.2.
into 10 raised to the power minus 3.
So it's 3.2. 3 point, सिर्फ 3.2 or anything else?
3.28.
3.28 into 10 to the power minus.
3.
So this is minus 3 moles. So 3.28 times 10 to the power minus 3 moles. The next thing is, so the board is hanging. Uh, the next part is they're asking for the 250 cm. How many moles would there be? So this was only found in 25 cm cube. So how many moles would there be in the 250 cm cube original solution? That would be 10 times this amount. So it's going to be the same number, except that it's going to be 10 to the power minus 2 moles. Okay, is this clear? That in the original 250 cm cube solution, you're going to have 10 times that many moles. And then you're being asked to find the moles of iron carbonate. Iron carbonate, all these moles are coming from iron carbonate. So we have the moles of iron carbonate over here. So use your answer to calculate the mass of iron carbonate. So it's moles multiplied by mr. So we already have the moles is 3.28 times the. I mean, what were the moles in the 250 cm cube? That's 3.28 into 10 to the power minus 2. And you're going to multiply it by the mr of iron 2 carbonate. Just be careful. Make sure you take the exact values given in the periodic table. It's iron, I think, is 55.8, and the other thing is carbon. That's carbonate would be 60, I think, because carbon is 12. Three oxygens, that's 16 times 3. What is the mass that we're getting?
61.8.
61.8 grams, and that's not possible because the original sample was 5 grams. Can somebody check?
3.80.
ठीक है, 3.80 grams. ठीक है, remember to use brackets properly in your calculator. So it's ठीक है, Bazga, I think you did not use brackets. So it's 3.80 grams. And now you have to find the percentage. So your original sample of spathos was 5 grams. And the mass that you're getting is 3.80 grams. That's the amount of iron carbonate in this sample. Into 100, what is the percentage that we get?
76.
The three significant figure. It's exactly 76, right?
Yes.
So 76.0%. You don't write 76. Make it up to three significant figures. And the question still continues. But that has nothing to do with the moles question. It says that iron ores containing iron 3 compounds can be analyzed using a similar method. A standard solution of an aqueous iron 3 compound is reacted with tin 2 chloride, and you have to write an ionic equation. So iron 3 compound is reacting with a tin 2 chloride. So we can write Fe3 plus reacting with tin 2 plus. And he's saying that you're getting tin 4 chloride and iron 2 chloride. So the product is tin 4 plus, and the other product is iron 2 chloride. So that's Fe2 plus. So that's your equation. But this equation looks balanced. But can anyone tell me what's wrong with this equation?
The number of electrons lost and gained are not the same.
Okay, the number of electrons lost and gained, they have to be made equal. Always check for that when you have a redox reaction. So you have tin 2 plus turning into tin 4 plus. That means it lost 2 electrons. And on the other hand, you have Fe3 plus, and that's turning into Fe2 plus, and that means it gained 1 electron, which means that the Fe's need to be multiplied by 2. And then the number of electrons gained and lost, they would become equal. So now the equation is balanced. Okay, always check for this. उसके बाद part 2, the part 2 is an excess of tin 2 chloride can be removed by the reaction of HgCl2. Uh, a white precipitate, so everything is given, and he's saying that an excess of tin 2 chloride can be removed by the reaction with HgCl2. So I think this one is tin 2 chloride, which they haven't written. That's tin 2 plus chloride Cl minus 1, so it's going to be SnCl2. And they've also given you the state somewhere. What was the state of tin 2 chloride? Tin 2 chloride is aqueous. It's written over here. So the state is probably aqueous. It's soluble compound. And the others, what about tin 4 chloride? Tin 4 chloride is also aqueous. So tin 4 chloride is it's also aqueous. This one is also aqueous. The only thing left is the precipitate, white precipitate of Hg2Cl2. That is the one that's going to be a solid. So we've written down the states as well. Now the next part of the question is over 1 million tons of hydrogen cyanide are produced each year using the whatever process. Draw a dot and cross diagram to represent the bonding in a molecule of NH3 and state the shape of the molecule. So that's easy, relatively. NH3 molecule. It's one N with three hydrogens. So can anyone tell me what the shape is?
Pyramidal.
Okay, so it's going to be pyramidal because it's a total of four electron densities. So it's derived from the tetrahedral shape, except that on one side there is nothing attached. So the top is missing, which is why it's a pyramidal shape and the angles are 107 degrees. And it's trigonal. It's a three-sided pyramidal shape. So trigonal pyramidal. And then
Very
they're saying,
different.
yes,
But isn't trigonal pyramidal an example of shape of molecules that have no lone pairs? Shouldn't
meaning
it
that
be?
have meaning if they don't have any lone pairs, it can't be pyramidal. But Minal, you're asking the question, right?
Yes.
Nini, can you repeat the question?
So, sir, there are two types of geometries that we study. One are distorted and the other are non-distorted. And the non-distorted ones are without lone pairs. So
Uh,
trigonal and pyramidal are two different shapes.
Nini, trigonal pyramidal is not two different shapes. There's trigonal planar and there's trigonal pyramidal.
So can we
ठीक है?
write trigonal pyramidal as
नहीं,
well?
trigonal simply means three-sided. ठीक है? It means it doesn't represent the shape. The other one that you're talking about is where you just have three bonds. ठीक है? The one that you're talking about, for example, BF3, that doesn't have a lone pair. It's just three fluorines. That's also a trigonal shape because it's just three bonds, but it's trigonal planar because all the molecules are. I mean, it's going to be completely flat.
Sir, I get it. Thank you.
Okay, so this is trigonal planar. They usually do accept. Sometimes they would accept trigonal, but remember this is the complete name, whether it's planar or whether it's pyramidal. Okay, if you have a lone pair on top, all the three bonds in the fan they would all start pointing downwards like this. So you have an HCN molecule, and they're asking the bonding uh, between the carbon and nitrogen atoms consists of one sigma bond and two pi bonds. Sketch the shape of the sigma bond and one of the pi bonds. What I'm going to do is, although the question is a lot simpler, what I'm going to do is I'm going to talk about this in detail about the hybridization of carbon. Remember, when carbon is bonded to just two atoms, it is sp2 hybridized. So that means that there's a carbon atom and there's going to be a sigma bond over here with nitrogen, and one of the orbital of carbon is going to get stretched would be stretched to the left side by a hydrogen atom. So electron density somewhere in the middle over here, but one over here. So carbon's bonds are getting pulled in two different directions, or orbitals are getting pulled in two different directions. That leaves us with two extra carbon orbitals because carbon has a total of four electrons. So there is one orbital, one p orbital, that is not used, and there's another one on the z axis. So two of the orbitals of carbon are spare. I mean, they're not being used. One got stretched in this direction. The other one went and bonded with this direction. Carbon had a total of four orbitals and 2pz1. So two of them they ended up changing shape. So they became your sp hybrid orbitals. So they ended up changing shape, and they got pulled in different directions. Two of them remain completely unchanged: the red one and the green one. Nitrogen also has a total of three orbitals. If you look at the electronic configuration of nitrogen, that's the outer electronic configuration is that it has a completely full orbital 2s2, and it has three orbitals which are half filled. They need electrons. Now, one of them got pulled in one direction by the carbon atom, so that still leaves you with two other orbitals, and these two other orbitals, they would be on different axes. Okay, for example, there's going to be one of the p orbitals would be parallel to one of the carbon orbitals, and they would end up forming pi bonds, and the electron densities would overlap. And then nitrogen has another spare orbital, which is the Z1, and that's going to be on the Z axis. So it's going to be on the Z axis. And that is also in parallel with the carbon orbital, so they would start to overlap in front and behind the axis. So on the back side, they would be overlapping happening as well. So this is how the bonding in HCN would work. In HCN, carbon is sp hybridized. One orbital got pulled in this direction, one got pulled in this direction, and carbon had two spare orbitals left: the 2py and the 2pz, the red one and the green one. For nitrogen, the case was exactly similar. Nitrogen had one orbital that was completely full, so that wasn't involved in bonding. It did not need any electrons. The other three needed electrons. So the 2px got pulled by the carbon atom. It ended up bonding over here. That left with two unpaired orbitals for nitrogen. One was the red one, the other one was the green one, and the two became parallel with the two orbitals of carbon, and they ended up forming two pi bonds, which is why you're getting a triple bond on one side. So you just had to draw in this molecule, just had to draw one sigma and one pi bond. And although you can't be expected to sketch this because that would be too difficult, it's a three-dimensional molecule. So they're probably going to just going to look for this thing, that you're going to draw an HCN molecule, and you're just going to show a pi bond. So you're going to show a pi bond between the C and the N. That's it. And you're going to label that. And there are actually two pi bonds. There's going to be another one which would be coming out of the page and going into the page. And the other one could be you're going to show a sigma bond where you can say that the electron density is over here on the axis between the two atoms. So that's your sigma bond. So you just have to draw rough sketches for this. Okay, is this clear? Mohammed, is this clear? Bazga, Ibrar, is this clear?
Yes, sir.
Yes, sir.
The next part is what is meant by the term dynamic equilibrium. It's just 1 mark, and the 1 mark answer for that is that the rate of forward reaction equals the rate of backward reaction in a reversible reaction. And you can add in a reversible reaction if you still have space. The next part is state and explain how the amounts of the chemicals present in the equilibrium mixture will be changed when the pressure is increased. So which equilibrium are they talking about? I think they're talking about this equilibrium. Uh, so where would the equilibrium shift if you increase pressure? Less gas moles or more gas moles?
Number of moles.
Yeah, I didn't hear this properly. Like it's going to be less gas moles. ठीक है?
Side having lesser number of moles.
ठीक है, so it's going to move to the right side where you have. Do you have? I mean, how many moles do you have? You have one, two. You have 3.5 moles over here.
Gonna shift to the other side.
ठीक है? I think they're 3.5. Let me just confirm. That's 3.5 moles, and the other side is 4 moles. All of them are gases, right? Only count the moles of gas. So all of them are gases. So if you increase pressure, it's going to shift to the left. It's going to favor the less gas moles. because if you increase pressure, what that does is that it decreases volume, so you can't really get more gas. So that's what you're going to write. Again, it's a 2 mark question, so you have to tell the explanation that the less gas mole side is favored, and then you're going to tell them that it's going to shift equilibrium position. It shifts to the left. The next part is the process uses a platinum catalyst, which increases the rate of reaction. Sketch a Boltzmann distribution on the axis given below, and use your diagram to explain how the platinum catalyst increases the rate of the reaction. So, what's the Boltzmann distribution of molecular energy? So, if you have a container, then all the particles in the container, gas particles, they are all at different energies, but most of them have energies that are very close to the average energy. Let's call this the average energy. So, the number of particles would be highest over here. So, the curve is usually skewed, and the number of particles having high energy, the number of particles are lesser. Okay, the height is the number of particles, and the number of particles at low energy, that their quantity would also be lesser. Okay, the height of the graph would be very low. Most of the particles have energy that's close to average energy. At average energy, the number of particles are, I mean, most of the particles in a container or in a room, they would be around the average energy of the container. For example, if the room is 25 degrees centigrade, then most of the particles would have 25 degrees centigrade. So, how would you show a catalyst? A catalyst, what you're going to do is you're not going to show a catalyst in the first place. What you're going to show is the activation energy. This is the activation energy. This is the minimum energy that is needed to start the reaction. So, how many particles have this energy? The high energy particles, it's these particles. These particles are the ones that have energy greater than the activation energy. So they have energy that is greater than activation energy. So that's very few. So that means all these particles over here, the low energy particles and the particles that are having average energy, they're not going to take part in the reaction. They're going to collide with each other, but they don't have sufficient energy. They won't be able to break the old bonds and form new bonds because they're not energetic enough. So only the few particles over here. So now explain to me, what would a catalyst do if you add a catalyst?
Reduces the activation energy.
Okay, so your catalyzed activation energy would be somewhere over here. So it reduces the activation energy. So that's with a catalyst. So now the energy that is needed, the minimum energy needed to start a reaction, that has decreased. Activation energy is lesser. So even these particles are now going to be able to take part in the reaction. So the number of particles, or the proportion of particles having energy greater than, so what you're going to write is that the proportion of particles, you're probably going to get marks for the graph. It's a total 3 mark question. So you're probably going to get 2 marks for the graph, 1 mark for this statement that we are about to write. So the proportion of particles having energy greater than activation energy increases. And because of that, you get more effective collisions or more successful collisions. So previously, only a very tiny proportion of particles was actually taking part in the reaction, but now you have a lot more particles that are taking part in the reaction. The next one, part D, is that hydrogen cyanide with propanone is an important first step in many organic synthesis. So we're talking about the reaction of ketones. Let's first revise what we studied in ketones. I think we did carbonyl compounds after that. So we're going to study all the reactions first. So carbonyl compounds. Carbonyl compounds are these compounds which are ketones or aldehydes. Cetyl bond O at the end, that's an aldehyde. In the middle, that's a ketone. Highly the kind of polar, not highly polar. They don't form hydrogen bonds, but they have permanent dipoles. So the melting and boiling points are higher than alkanes and alkenes, but lesser than alcohols and carboxylic acids. Plus, they're very soluble, slightly soluble, not soluble. Uh, they take part in oxidation reduction reactions. We're going to talk about that later. This is the reaction that they undergo, which is nucleophilic addition. You need HCN and you need NaCN catalyst. What happens is that the ketone or the aldehyde, the positive carbon gets attracted to the nucleophile, which is CN minus 1. The negative ion is going to be attracted to the positive carbon atom. And as it is attracted to it, it bonds with it. And when the negative ion comes close to it, the electrons or the electron cloud over here, it gets repelled and O minus 1 over here is formed, which then attracts H positive again and ends up forming an alcohol, which is known as a cyanohydrin. So the question is about this. So if we go back, give the full name of the mechanism of this reaction, and the name of the mechanism of this reaction is nucleophilic addition. And the other thing is complete the diagram. So you're going to complete the diagram, which is that this carbon is partial positive. The CN minus one with its lone pairs are going to be attracted to this. They're going to be attracted to this positive carbon atom, and the electrons over here are going to be repelled because of that. And the next step is that there is CH3, and O minus 1 is formed. And the next step after that is, now you have two options. Uh, Two acceptable options are there. One is that you can either write HCN or you can just write H plus 1. So the positive H is going to be attracted to the lone pairs. And because of the negative charge, the electrons over here are going to be repelled. So the end result is that you would have the CN was already there. Now you have an OH. And the CN minus 1 catalyst is reformed or formed again. You started off with CN minus 1, you again got CN minus 1. The reason you added NaCN was because HCN doesn't really ionize. But during the mechanism of the reaction, uh, the first CN usually comes from the catalyst, which is NaCN. So that's your mechanism. And then there's question number 4, which is give the molecular formula of G, so that you can try and figure that out. It's going to be how many carbons? That's 2 plus 2. I think that's 4. And H would probably be 10. That's 4 hydrogens in the middle, and there are 3 and 3, so that's 6, so that's 10. Then you have to give the empirical formula of compound H. You need to total the number of carbon atoms. It's going to be 3 carbons over here, 4, 5, 6, and 7 and 8. And you can count the number of hydrogens. That's 9 plus 2, that's 11, plus 1 is 12, and then you have 6 hydrogens, so that's 18. So it's C8H18, and the empirical formula would be C4H9. And for the last one, you have to give the skeletal formula. The skeletal formula only looks at the carbon atom. So that's 1, 2, 3, 4, and so those are the carbon atoms which I've circled. So it's going to be that's the first carbon atom, second carbon atom, third carbon atom. On the middle carbon atom, there's another carbon atom. So that's, and on the last one, there's again another carbon atom. And from second from the last, there's an OH. So that hopefully is your skeletal formula. So that's 3, 4, 5. So that's 1, 2, 3, 4, 5. So that's 5 carbon atoms. Okay, is this clear?
Yes, sir.
Next is write an equation to represent the complete combustion of compound H, which you can probably do. Carbon dioxide H2O would be produced. Fossil fuels are contaminated with sulfur. State and explain why. So state and explain why fossil fuels that contain sulfur pose a problem. What's the environmental problem with sulfur?
Is it acid rain?
It's going to be acid rain.
Dissolve in water and form.
Okay, so the first thing is you're going to write about the combustion that the sulfur would burn up, because it's if you use it as a fuel, SO2 would be produced, and that SO2. Uh, so I'm going to go into the whole detail. Uh, what happens next? SO2 combines or gets oxidized by NO2 in the atmosphere, and what happens is the sulfur oxide turns into SO3. The NO, which is gets oxidized in the atmosphere again, back again. So it's acting as a catalyst. NO2 is acting as a catalyst. And then what happens, the last part is that SO3 reacts with water, rainwater, and ends up forming H2SO4. And the same pretty much happens with NO2. It also reacts with water to produce two acids, nitric acid and also nitrous acid. So both acids are produced. So probably in this question, they weren't even asking for the whole explanation for acid rain. What they were probably just looking for was the word acid rain and its environmental that oxides of sulfur. And why do they pose a problem? Because soil and water bodies would become acidic. There were three types of problems associated with acid rain. One was the problem with on human health. It causes skin and eye irritation. One was the problem with buildings. They corrode buildings, limestone, and things made out of metal, bridges, etc. And the third was the environmental consequence, and that soil and water bodies, they become acidic. So you're just going to write that oxides of sulfur are going to mix with rainwater to form acid rain. And so next is the boiling points of compounds G, H, and J are shown below. Explain the differences in the boiling points of the three compounds. As you can see, J has the highest boiling point, so you have to give a reason for, and G has the lowest. So J has the highest, and G has the lowest. What's the reason? Why does J have the highest boiling point?
Because of the permeable
Because
dipole.
it has hydrogen bonding.
Okay, so it has hydrogen bonding. It's a highly polar molecule. The oxygen has its lone pair, which makes it plus it's electronegative as well. So that makes it really, really negative, and H is partial positive. So it has hydrogen bonding, and it's one of the strongest intermolecular forces. So you're going to write strong intermolecular forces. Hydrogen bonds are present. Why is the other one the lowest? What type of intermolecular force is there in this molecule?
Van der Waals forces.
It's a carbon and hydrogen bonds are non-polar, so it has only van der Waals forces, which are very, very weak. But did they ask us about, because it's a 4-mark question, we probably have to comment on the third one as well. Why is this so close to the I mean, look at its boiling point. This is 99 degrees centigrade. This is almost the same as J, which was, I think, 112 degrees centigrade. So why are they so similar? Which intermolecular force is present in H?
Van der Waals forces, but this is a larger molecule, so it will have more van der Waals.
See, it's going to have more electrons and it's going to have more van der Waals forces. Okay, so you're going to comment because it's a 4 mark question, so probably comment on this as well. So it also has van der Waals forces, and since it's a bigger molecule and has more electrons, so there would be more temporary dipole induced dipoles. So more temporary dipole induced dipole attraction would be there, which is why it's almost the same as the hydrogen bonding molecule, because that molecule is small. It only has 5 carbon atoms. This one is bigger. It's 8 carbon atoms. So van der Waals forces, they vary with the size of the molecule. So then you have compound J can be produced from 2-chloro-2-methyl butane. Give the reagents and conditions. So they ask you for J. J has an OH. First thing is we need to figure out what this molecule is. 2-chloro-2-methyl butane. So it's butane. So that's 1, 2, 3, 4 carbon atoms, and it's 2-chloro-2-methyl. So on the second one there's a chlorine, and and on the third one there's a methyl, which is 1 carbon atom. So it's CH3. So all you have to do is you have to get rid of the Cl and substitute it with OH. That's a reaction of halogenoalkane. That's a nucleophilic substitution reaction. So let's I mean it's right over here. Yeah, actually it's not here. 1 second. Do we have halogenoalkanes? 1 second. The answer to this is NaOH aqueous, but just this one, this board over here. Just 1 second. So where did it go? This one. So halogenoalkanes, just a quick revision of halogenoalkanes, that how many reactions did we have for halogenoalkanes? There was formation of halogenoalkanes, which was free radical substitution of alkanes, chlorine and bromine UV light. And then there was electrophilic addition of alkenes, where you had bromination and HCl, etc., getting added to the double bond, and they would form halogenoalkanes. And then alcohols could get substituted to halogenoalkanes by adding different reagents. PCl3, PCl5, SOCl2 can be added to form chloroalkanes. Now this one, we're talking about this one. If you want to get rid of the Cl and you have to put an OH in its place, it's going to be NaOH aqueous and reflux. If you want to get rid of the Cl and put a Cn-1, that's NaCN ethanolic, or NH3, that's NH3 and ethanolic plus reflux. So 3 different nucleophilic substitution reaction mechanism, and the mechanisms were that for primary halogenoalkane, the carbon over here had a very strong partial positive charge, which meant, and why did it have a strong partial positive charge? Because it was surrounded by hydrogen atoms. They don't have electrons. Uh, so, and they don't have electron donating effect, which is why the positive charge was very strong, and which is why the OH nucleophile or any nucleophile Cn-1 or NH3 would be very strongly attracted, and bond formation and bond breaking would happen simultaneously. Both things would happen simultaneously. The OH would be bonding with the carbon atom, and the Cl at the same time would be getting repelled. So the result would be that a transition state would happen where the carbon would be partially bonded to 5 atoms, and it would be highly unstable. Cl would break off. That would leave you with the alcohol, with the OH. And it was a one-step reaction. Now, for tertiary halogenoalkanes, what would happen was that the carbon, which is positive, but it's surrounded by big groups, large carbon chains. So it's surrounded by electrons. So the positive charge is not very strong. And if the Cl wants to take away electrons, the Cl-1 would be easily, heterolytic fission would easily happen. Why? Because the positive charge or the carbocation that's going to be formed is not going to be a very strong positive charge, because it's surrounded by electrons. So even if it becomes electron deficient, it becomes positive. The charge density is going to be very low because electrons from all sides are going to be pulled towards this positive carbon atom. So the positive charge over here is not going to be very strong, and which is why the carbocation is going to be very stable, and it would allow the Cl minus one to break off. Uh, and then if the OH concentration is significantly, or the nucleophiles are in a significant amount, the nucleophiles would come and they would get attached, and your alcohol or your nitrile or your amine is going to be formed. And this was a two-step reaction. So in this one, the Cl breaks off first, and then the nucleophile comes and gets attached to it. Uh, doesn't happen simultaneously like in the previous case. In the SN2 mechanism, in the primary mechanism, all this thing was happening simultaneously. But over here, it's going to be two distinct steps, and it's a two-step reaction. So he's talking about, in the question, he's talking about this reaction, that you have to get rid of the Cl and put an OH over there. So it's going to be, the reagents and conditions are going to be that you're going to use NaOH aqueous plus reflux is going to be used. Now, after that, this is probably the last question, which is that some reactions of compound P are given. The first, and you probably have to give the organic structures for compound Q, R, S, and T. So we'll just do this over here. Now, the first one is, uh, it's cold acidified KMNO4. Now, if you look at this molecule, what does cold acidified KMNO4 do? What it does is that it oxidizes alkenes. So there is an alkene over here. Ketones are not oxidized. Remember that. Ketones are resistant to oxidation. So you have a double bond over here. The double bond is going to disappear. The double bond will disappear, and in its place, what's going to happen in its place is it would change into a single bond, and diols are going to be formed. That's one very important reaction of alkenes. Alkenes underwent two types of oxidation. One was mild oxidation. The other one, let me find out if I have the alkene board open. Just 1 second. So probably over here in this, this one. Let me add the. Okay, so alkenes, mild oxidation, cold dilute alkaline KMNO4. If you use that, uh, nothing would happen except that the double bond would turn into a single bond, and OH, it's like an addition reaction. Two OH groups are going to get added to the double bond. So if you have double bonds in a molecule, the double bonds would go away, and the carbon atoms, OH groups, would get added to it. And then you had strong oxidation. Strong oxidation, you used hot concentrated acidified KMNO4. And what happens in strong oxidation is that the double bond completely breaks into pieces. And when it breaks, you have three scenarios. One is that the carbon in the double bond was bonded to two hydrogens, so it changes into carbon dioxide and H2O. The second scenario is the double bonded carbon atom had just one hydrogen and one carbon chain. That would change into an aldehyde and then a carboxylic acid. And the third one was, if it's bonded to two carbon chains, it's going to change into a ketone. So some examples were, for example, if you have a propene molecule, the double bond is going to completely break in strong oxidation. This side is bonded to two hydrogens, that's carbon dioxide and H2O. This side is bonded to on one side by a carbon chain, so it's going to be carbon chain plus this carbon would change into a carboxylic acid. Pretty much the same happens to bigger, more complicated molecules. There was a double bond here. This changes into carbon dioxide and H2O. This one over here changes into a carboxylic acid, which I've drawn over here. These two sides, the double bond breaks. This one, there's only one carbon chain attached, so that's a carboxylic acid. This side has two carbon chains attached, so this side is turning into a ketone, which you can see over here. So that's a strong and mild oxidation of alkenes. Now over here you have cold, which is mild oxidation, which is why you're going to get diols. Now in these two parts, reduction is happening. Uh, NaBH4 is used to reduce ketones. So this was about alcohols, the oxidation reduction of alcohols, which we probably did somewhere over here. I think this is more about. Okay, so oxidation of alcohols. Where's reduction? Okay, this is reduction. That carboxylic acids can be reduced to aldehydes and aldehydes can be reduced to primary alcohols. And the same with ketones, they can be reduced to secondary alcohols. Uh, and they could be oxidized as well. Primary alcohols can be oxidized to aldehydes and they can be oxidized to carboxylic acids. Secondary alcohols can be oxidized to ketones. Okay, so the oxidation part is over here. These are all the oxidizing agents. To turn an alcohol into an aldehyde, you need dichromate 6 and KMNO4. The same for aldehyde turning into carboxylic acid, but two more can be used. Toluene and phenylene could also be used. For secondary alcohols, it's the same oxidizing agent except that they change into ketones. Anyway, so this is reduction happening. Now, NaBH4 is used to reduce ketones. So it's going to change into the double bond stays there. The ketone part changes into an OH. That's it. It turns into an alcohol, back into an alcohol. Oxidation, the secondary alcohol would change into a ketone. A reduction, the ketone would change back into a secondary alcohol. Then over here, it's nickel plus H2. That's something that reacts with alkenes. That's hydrogenation. So in this case, what happens is that the alkene, it's an addition reaction. H would get added to the double bond, and the double bond would break or turn into a single bond. So nickel and H2 is used to reduce alkenes, but it sometimes also reduces ketones as well. That the double bond over here could go and it could turn into a secondary alcohol as well. So H2 and nickel mainly used to reduce, or it's used in the hydrogenation of alkenes, but they can also be used to reduce aldehydes and ketones as well. And the last part is alkaline aquasidine. Now this one is the iodoform test. Okay, that's your iodoform test. And what is your iodoform test? The iodoform test is a test for a certain structure. The certain structure is that the molecule must have exactly this thing. It must have a ketone or an aldehyde next to a CH3, sealed bond O next to a CH3, or it must have an OH next to a CH3. So if these two structures are present, only then would the molecule, would the iodoform test be positive. And in both cases, what happens is that the R group breaks away, not the R group, the CH3 group breaks away. The CH3 group turns into a precipitate of CHI3, which is a yellow precipitate. So CHI3 turns into a yellow precipitate, and the rest of the molecule changes into a carboxylic acid. The C, in both cases, would change into a carboxylic acid, but since it's an alkaline condition, you would probably get a salt of the carboxylic acid, not the carboxylic acid itself, because the conditions are alkaline. They're using OH minus 1 ions, probably NaOH or KOH. So you're going to get a salt. So what is compound T? So we're going to apply the iodoform test. Can we apply the iodoform test in the first place? So if we draw the molecule, it's CH3, then there is C double bond O, and then there is another CH, I think just a CH, then a double bond, then another CH, then a CH3. So that's the molecule. And does it have this structure? It certainly has this structure. It's a CH3 next to a C double bond O. So that means this part would break away and form from a yellow precipitate of CHI3. And the other part would change into I mean, they've already drawn that. It's going to change into a carboxylic acid. It's going to change into CH3, CH, there's a double bond, then CH, then there is C double bond O, and O minus 1. A salt would be produced instead of the carboxylic acid, which is already shown over here. So compound T is the yellow precipitate. It's triiodomethane. That's the thing that's going to be produced in this reaction. So give the name of the compound P, which is triiodomethane. P. So you have to give the name of compound P. How would you name that? What would you call this? Can anyone name this?
Is it pentuone or pentuinone?
Okay, so this one is pent 1, 2, 3. So how many carbons does it have? Let me mark them. So it's 1, 2, 3, 4, 5. So it's pent. Which of there are two functional groups in this? There's a ketone and there's an alkene. Which one has a higher precedence?
Ketone?
Okay, the ketone has a higher precedence. Remember the precedence order that carboxylic acid sit right at the top, and then you have your ketones and aldehydes, and then come the alcohols and amines. So ketone has a higher precedence. So you're going to try and give ketone the smaller number. So all the counting must be done from this side. So the name of the molecule is going to be it's obviously pent, and it's pentanone basically. But since it's unsaturated, so instead of the an you would write en. So it's penene. This is at
Can we write that?
4 3.
Can we write 3 pentan 2 on?
No, you can't write that. Remember, for alkenes, whenever you have an alkene, okay, the an would change into an en, and you would write the position next to it. Okay, I mean, without the double bond, it was pentanone, right? Uh, so then for alkenes, remember any molecule, whether it's a carboxylic acid, ethanoic acid, the an in ethanoic acid would change into en. Whether it's a alcohol, if it's pentanol and there's a double bond, the an in the alcohol would change into an en. Okay, Minal, is that clear?
Yes, sir.
And since it's a ketone, so the suffix is on, and the position is 2. You're going to count from this side. Ketone has a higher precedence. You give it a smaller number. So you count from this side. So this is ketone is at number 2, and the alkene would be at the third carbon atom. So it's going to be 3 en and 2 on. So that's the name of this molecule. Is this clear to everyone?
Yes, sir.
So it was pent 3 en, and you had 2 on, right? So anyways, moving to the next one, what would you observe in compound P reacted with 2,4-DNPH? 2,4-DNPH dinitrophenyl hydrazine. That gave a positive test for aldehyde and ketone. So you're going to get an orange precipitate. Okay, what was 2,4-DNPH? Where's our aldehyde and ketones? Okay, somewhere over here. This one. So carbonyl compounds, this was used as an identification test for carbonyl compounds, which was 2,4-dinitrophenyl hydrazine. It's this molecule over here. It's a benzene with 2 NO2 groups. So that's dinitro. And then there's this hydrazine part. What would happen is that the ketone or the aldehyde, the C double bond O part, would join up. And it's going to be a condensation reaction. A water molecule is going to be produced, and the C over here would then directly form a double bond with the N over here. So this is your orange precipitate that's going to be formed. Okay, so the observation is that you get an orange precipitate. So now this one. Now this is a very tough question actually. This last one. Uh, I think so. Uh, if my memory serves me right. I said this question over here. Now you have to, and I think this question has nothing to do with the rest of the question. He's saying the compound U contains a chiral center and has the same molecular formula as compound P, which is C5H8O. So, so you're dealing with a compound which is C5H8, H8 and O. Now you have to solve this question like a puzzle. So C5H8O, and he's saying contains a chiral center. So there is one carbon in the molecule that is chiral, which means that it would be bonded to four different groups and it would be forming two non-superimposable mirror images. Anyways, compound U readily decolorizes a sample of bromine water. What information do you get from this first statement?
Unsaturated?
Okay, so it's unsaturated. That means there's a carbon double bond carbon present as well. So that's another thing. Compound U does not show cis trans isomerism. So that means it's the type of double bond that doesn't have a cis and trans. No geometric isomers. Okay, so it doesn't have geometric isomers, which means that that the sides of the carbon atom they would be the same, which means the switching would not actually make it an isomer. Would not there wouldn't be any geometric isomer. For geometric isomers to happen, the double bonded carbon atom must be bonded to two different groups, and on this side as well, they must be bonded to two different groups. So in this case, there is no cis trans. So around the double bond, the carbons are attached to probably the same group, or at least one of the carbon atom out of the two is attached to the same group. ठीक है, Ibrahim, is this clear? Ethan, is this clear?
Yes, sir.
Okay, so the next part is when compound U is heated in a reflux in the presence of excess acidified potassium dichromate 6, the organic product gives the infrared spectrum. So he's oxidizing. What is he doing to compound U? He's potassium dichromate 6. So that's oxidation happening. And this is the oxidation product. So dichromate 6, who do you oxidize with dichromate 6? You can oxidize a lot of things. You can oxidize a primary alcohol. You can oxidize a secondary alcohol, or you can oxidize an aldehyde. Right? Plenty of things can be oxidized with dichromate 6, uh, probably given over here. Right? Primary alcohols with K2Cr2O7 turning into an aldehyde, and they can be oxidized with K2Cr2O7 as well to carboxylic acids. Secondary alcohols can be oxidized to ketones with K2Cr2O7. So, so, so your compound C5H8O is one of these things, and the oxidation product is given. So you're given the infrared spectrum. I mean, now you have to figure out what the oxidation product is. Now, if it's a primary alcohol, the oxidation product could be a carboxylic acid, or it could be an aldehyde as well. If it's a primary alcohol, if it's a secondary alcohol, then it's going to be a ketone. And if it's an aldehyde, then it's going to be a carboxylic acid. So you need to figure out whose infrared spectrum is this? Is this an aldehyde or a carboxylic acid or a ketone? That would give you an idea of what type of organic product this is. So open the data booklet. Now, if I have 1 second. Chale, this one is where's the infrared spectrum? Remember infrared spectrum. The background is that bonds vibrate. Okay, the bonds are not rigid, and the bonds vibrate and they absorb frequencies. They vibrate because of frequencies in the infrared spectrum. So I think this is the infrared spectrum, right? Now, if you look at, so we'll compare this. If you look at around 3000, you have this very broad absorption. So why do you get a broad absorption around 3000? Uh, let's open it and look at the OH groups. There's only one absorption that's the appearance of the peak. There's only one broad absorption, which is this one, the one that I'm pointing to. And that's the OH in the carboxylic acid. So I'm going to go back and it's around the 2500, 3000 mark. And we're getting in that range as well. And there's only one strong and broad absorption in the spectrum, and that's because of the OH group, but the OH group of the carboxylic acid. So go back, and this is due to the OH in. Okay, that's what the data booklet is suggesting. I said then there's this very strong absorption at around the 1700 mark. So open the data booklet. Remember the serial bond O. That's a strong absorption around the 1600 mark, uh, and the appearance of peak is strong. So that's your serial bond O, right? So that's your serial bond O. So that pretty much confirms that the product is a carboxylic acid. So that confirms the product is a carboxylic acid. But that leaves you with two options. It's either going to be a primary alcohol or it's going to be an aldehyde. So that's what we are getting at. So we don't know whether it's a primary alcohol or it's an aldehyde. So is this clear up to this point? Do you understand why this is a carboxylic acid? Is this clear? Ethan, Mohammed, is this clear? Mazga, is this clear? Minahil?
Yep.
Yes.
So that pretty much sums it up. Use the information to suggest a structure formula for compound U. Now, based on this, figure out the structural formula of Q. So it's all guesswork. You have to draw. It's trial and error. Draw a molecule, 5 carbon atoms. It's supposed to be an alkene. So make sure it's an alkene. Let's say put the 5 carbon atoms in a straight line. The alkene must not show cis and trans isomers. So not showing cis and trans isomers. So both of them are H. So no cis trans there. It should be an alcohol or it should be an aldehyde. A primary alcohol. The primary alcohol the OH would be somewhere in the middle, not in the middle, at the end. So let's go with primary alcohol for a second. What I'm going to see now is, do I get the right number of hydrogen atoms? Can you count the number of hydrogen? It should be 8. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that means I can't really go with an alcohol. Let me try making it into an aldehyde. So if I make it an aldehyde, do I get the right number of hydrogen atoms? It's 1, 2, 3, 4, 5, 6, 7, and 8. So that means I should not be going with a primary alcohol because with an aldehyde, I get the right number of hydrogens. Okay, is this clear as well up till this point?
Yeah.
Yes.
Achha, but then, so how many things, no cis trans, that's met. Okay, that's done. Aldehyde, I've figured that out. No cis trans, that's figured out. But they're saying that it's going to be chiral as well. So the same thing, try and make this chiral. At the moment, it's not a chiral molecule. There's no carbon atom. So I'm going to try and make this a chiral. So I'm going to sort of make it a branch structure. Maybe shorten the chain. It's 1. So I'm taking 1, keeping everything the same. I'm just shortening the chain so that I can have a branch. So do I have 8 hydrogen atoms? I think I do. So that's 1, 2, 3, 4, 5, and 3. That's 8. This carbon is now So this carbon over here is now chiral as well. So I have a chiral carbon atom in the middle of the molecule as well. So that pretty much sums it up. It's an aldehyde. So it's going to get oxidized into a carboxylic acid. So that statement is also met. It's an alkene, unsaturated, but it also does not show cis trans, and it's a chiral molecule and it fits the formula. So is this question clear?
Yes, sir.
Yeah,
The number of hydrogens like C5, H8, and O. Could we say it right in the beginning that this molecule cannot be an alcohol? Could we say it right in the beginning?
no, you have to test it out because whether you have with a double bond and with an alcohol, you can't really figure out how many hydrogens it has. You have to draw it.
No, in order for it to be an alcohol, shouldn't it be 9 hydrogens, but there are 8?
No, listen. The general formula is not going to work. The reason it's not going to work is because it's also an alkene.
So yes, okay.
ठीक है वो जो the general formula which was CnH2n plus 1 NOH, that only works if for simple alcohols and alcohols only. ठीक है because it was an alkene also, so the general formula is not going to work. चलिए ठीक है, I think this was the last question of the paper. So this is just mark this paper somebody, ठीक है. It's it's I think February March. Which paper is this? It's February March 16 question paper 2. So let's continue this next time. Okay then.
Thank you, sir.
Thank you.
Okay, bye bye.
Love this, sir.
Allah Hafiz.